Okay, ladies and gentlemen, 4 o'clock. Welcome back to your favorite class. Yes. We're going to finish mass moments of inertia today, and that is the last bit of information you'll be responsible for exam number 1, which happens to be next Thursday. It'll take place in class. More specific details to come. I'll put together a document with all the information about the test and send it out to you guys on Canvas, and you can take a look. But basically, the idea is you're going to take your exam at a comfortable place for you, with your laptop in front of you. I'll distribute, you'll do your test, you'll hand it in. That's the basic idea. I will not be here in this room for your exam, but you can come take the exam in this room if you want. All right. You have a homework number 4, which is on mass moments of inertia, which will be due next Tuesday. Definitely after we do our last little mass moment of inertia problem here today, you should be able to do everything on that homework. So that's that. I did post a set of practice problems for exam number 1. There's a lot of practice problems there, and I have my full handwritten solution for those practice problems. So make sure to take a look at that. I'll tell you, if you can do all those practice problems easily without too much trouble, you will dominate the exam like a grape betwixt your tiny fingers. Okay? So do all those practice problems, crush them like a grape, and then you will crush the exam like a grape. All right? So do that. Right. Let's pick up where we left off. Get my notes here. What class is this? Where am I? Okay. Here. So last we left off, we were looking at parallel axis theorem, and specifically we were finishing our cone example by looking at what is the mass moment of inertia of this particular cone about its own centroid. So we had done with direct integration, calculation of the mass moment of inertia about sort of an axis that passes through the tip of the cone on this backside. And then I was asking you, or we were doing an example, where we were relocating the mass moment of inertia or calculating the mass moment of inertia about the centroidal y-axis, given information that we had about sort of this arbitrary y-axis out in space, and knowing that it's located at 3/4 h along the way. So that's about where we left off, talking about parallel axis theorem and going through this example. And we had sort of finished by looking and writing here that your area moment of inertia about the y-axis for this cone has this general expression. All right. So let's move on with the notes and a little bit of information, some final little bits of information about mass moments of inertia. And then we'll do one last example problem with composite bodies, and then we will close the book on all things related to not motion in this class. And we will finally do dynamics, finally. All right, so away we go with the last bit of information about mass moments of inertia, and that's composite bodies. And we've already done this for area moments of inertia, so you probably kind of already know where I'm going with this. But the idea for mass moments of inertia of a composite body would be that you happen to have some random shape that is made up of arbitrary shapes that you sort of know the mass moments of already. So what do I mean by that? Well, you can calculate what the mass moment of inertia is of a body made up of many bodies that you might already know the mass moments of inertia of. So I'll just say similar to centroids and area moment of inertia. The mass moment of inertia of a composite body about a particular axis. May be calculated by summing the contributions of the individual bodies in the composite. by summing mass moment of inertia contributions of each individual body. Okay. Right, so a very simplistic example might be like if you had a coordinate system that looked like this, x, y, z, and let's say you had some plate here. Okay. And then on top of that plate, you had a thin disk. So on top of your plate, you've got some, I know maybe I should have done this in red or something a little bit more easy to see, but on top of it, you've got some other sort of thin disk on top of it. I know, not the best picture. Sorry about that, but thin disk. And here's your flat plate. Okay, so let's call the thin disk object number 2. And we can call the flat plate like object number 1. And in math speak, we would have something like mass moment of inertia of some object about the x-axis is the contribution of the mass moments of inertia of the individual objects about their own axes, where I here going from 1 to n, where n is the number of bodies. This is how you would write it in math language. Mass moment of inertia about y is y equals 1 to n of the contributions of each of the individual components. Each of the individual components, where n is number of bodies. Okay, in this example over here, n would be 2, body number 1, body number 2. We could sort of refine these guys if we want, even though I don't sort of put this in the PowerPoint notes. We know that the mass moment of inertia of each individual object can be written as something like the mass moment of inertia of that particular object about its own centroid plus the mass of that object multiplied by the distance that that object is squared away from its axis of interest. Okay. So if we had more information on our example here, let's say we're looking at like the z-axes of these two bodies and they happen to be right on top of each other. So let's say this is the z-axis for object 1 and for object 2. And this is like the centroid of both of these objects. Well, you can look this up in a chart. But the mass moment of inertia for object 1 about its own like centroidal z-axis is 1/12 the mass times the dimensions of this particular plate, which would sometimes be called b squared plus c squared, where this would be like side b. This would be like side length c. That's for a flat plate. You can find that in any sort of chart. And for object 2, it's 1/2 mr squared, where r is the radius of the plate. So if I wanted like the mass moment of inertia of the composite body about, the centroidal axis of that composite, and I'll just add these two guys together, and that would be the total mass moment of inertia about the z-axis of that particular body. If I wanted it about this like global z-axis, which is kind of in the back of the square and the circle there. Well, I'd have to figure out like what is this distance between the centroidal axes of those two individual objects and the z-axis of this arbitrary coordinate system. Looks like that's just, you know, square root of b squared plus c squared, if I had to look at that. But if I knew that distance, I could just use the parallel axis theorem to resolve each one of those individual components into the z, y, or x directions. Okay. So you've seen this for area moments of inertia. You've seen this for centroids. It shouldn't be too wild and crazy of an idea. And I want to do one full-blown example problem where we look at calculating the mass moment of inertia of a composite body. And this is sort of the last slide of your mass moment of inertia notes. I'll just bring that in here straight away. So here is the problem statement. And I'll bring in the picture here as well. Whoa, why did I put it way down there? Never understand like copying and pasting into this like OneNote. Yeah, that worked just fine. Okay, I realize this is kind of a complicated example problem, so I'll give you a second if you want to copy this. For those of you kind of taking notes by hand, give you a minute while I have some of my energy juice. Maybe let's not do all the coordinate axes. Just do the y-axis. It'll get the point across. Specific. The mass moment of inertia. English units, my favorite, except for one thing. Not my favorite. You guys like do English units in thermodynamics? Talking about like BTU, horsepower, foot squared and stuff. Oh my God, it's horrible. Feel bad if you're taking thermal right now. Horsepower, like that doesn't even make it like. Yeah, it's like Bill, the one horse that they measured his particular power one time. He became the standard. Bill the horse. And they still like use horsepower as a metric for like how powerful things are. It's like this rocket has 1,000,000 horsepower. It's like, why are you even using that unit? Like, what do you expect Bill to get 1,000 of his friends to like all of a sudden start moving this rocket? Like, come on. 1,000,000 friends, that's a lot.
To be honest, I don't understand why they just change it. Like,
Yeah, I don't know why the Americans don't adopt the metric system. Well, I do know why, and that's because it would cost a lot of money to change, but that's only one thing. There's too much inertia for the English system. Oh, how do you like that one? Yeah. Yeah, what is the mass in English units? I'm glad you asked. You're going to find out right now. All right, so let's as they say in Mulan, let's get down to business. So we can see here that we have kind of a strange looking forging. Maybe this is some machine component for, I don't know, hooking two pieces together through pins. And this is made up of what's obviously three easily identifiable composite bodies. Let's say that this object here, this is object number one, it's like this rectangular prism. We have this object down here, which is like object two, which is a right cylinder. And object down here, or up here, I'll call object three, which is also a right cylinder. Object two and three are more or less the same dimension. They're actually going to end up contributing the same to the mass moment of inertia about y-axis, and we'll show why that is in just a second. Okay. Now, the idea is that each one of these objects, you could go to a table in your book and figure out what is the mass moment of inertia of this particular object about its own centroidal axis. It's pretty straightforward and pretty easy to do. So let's draw in here some what would be centroidal axes of each one of these objects. For object number one, we're like the XYZ coordinate system they give us is already like the centroidal XYZ system, okay? So nothing additional required here for object number one. These axes here are the centroidal axes of object number one. All right, so that's nice. Objects two and three, if these are homogeneous cylinders, then their individual centroidal axes will be located in the center of those cylinders. Something like this. I'm going to try to keep the clutter to a minimum, but if you want to write like, I don't know, maybe it's helpful to do like x of object 3, y of object 3, z of object 3. Okay. Now, how are we going to attack this problem? All right, well, we know that the mass moment of inertia of this total composite body is going to be the summation of the contributions of the individual mass moments of inertia of our three composite pieces. So here I is 1, 2, 3, where we have, you know, object 1 is the prism, and 2 and 3 are the cylinders. Okay. So let's go through and think about what the mass moments of inertia of each one of these individual pieces would be. And we want to keep in mind that we know what they are about their own centroids, but we're really interested in what is the mass moment of inertia of this object about this global y-axis. So we always have to sort of keep that in our mind. All right, so for this object 1, this is a rectangular prism. So you can kind of, like I said, go to your book or go to the notes that I provided to you and take a look at what is the formula for mass moment of inertia of a, you know, typical rectangular prism. So you can go in your notes here and take a look at, if you have a rectangular prism that's dimensions A by B by C, which is kind of what we have here, and we can define A, B, and C going back to the image in just a second. We're note here that this particular image shows us that the mass moment of inertia about an axis that pierces through like the long axis of this rectangular prism is 1/12 the mass times the dimensions of the cross section B by C, which is perpendicular to this axis. All right, so our general formula for this particular rectangular prism, if we think about the analogy here, is that we have this axis, y-axis that we're interested in, that is like moving through our prism here, as you can see. And the cross section associated with the axis and the plane that's perpendicular to that y direction is going to be 2 by 2. All right. So I'll write my general formula for object 1 is going to be the mass moment of inertia of that object about its centroid, expanding here to include the parallel axis theorem. just to be very clear about what's happening here. And we said that the mass moment of inertia of this first object about its own centroid, we just looked it up, is something like 1/12 mass times this b squared plus c squared term. All right, so this is like your I bar y1. Plus my mass, I don't really have that quite yet, but let's just put that in here as m. And this d squared. All right, remember for the parallel axis theorem, this variable d, this is the distance between the centroidal axis of object 1, which is this rectangular prism, and the axis of interest about which we are looking for our final result. Well, in this situation, my y-axis happens to just be the centroidal axis of object number 1. So in this particular situation, we don't really have to apply the parallel axis theorem here because our distance from the y-axis of our global coordinate system to the y-axis of our centroidal object 1 is 0. So here, md squared going to 0. All right, but I still have some issues here. And that is, I don't, at this point, know the mass of my rectangular prism. So we need to calculate that. All right. In the problem statement, we're given the specific weight of this particular steel, 490 pounds per foot cubed. So if we figure out the volume of our rectangular prism here, we can convert and get the weight of this prism and then use gravitational constant to get us the mass of this prism. All right, so need mass. My volume here is just base times width times height, rectangular prism. Okay. So we go back up to our image here, 2 inches by 2 inches by the total height here. It's a little bit difficult to tell by this image, but the total height is 3 inches in this direction and 3 inches in this direction. So a total height of 6 inches. So here's this 2 inches times 2 inches times 6 inches. Here's the 24 cubic inches. We're given our specific weight in terms of cubic feet, so we need to convert here. Um, 1 foot is 12 inches, and I'm cubing this. This is going to give me a volume of my piece of 0.0139 cubic feet. Right. Now I can convert to weight. Using the sort of conversion that I was given in the problem. All the way back up here, it's 490 pounds per cubic foot. And give me something like 6.81 pounds, which is unfortunately not a mass unit. English units, I tell you. Guillerme's got to be like, why did I come to America to study? God. He lives in Brazil normally. Doesn't even have to deal with this nonsense. Right? So if we want a mass, 6.81 pounds times. Here, we're going to convert to slugs. God. And basically, it's just the division by gravity. So 32.2 feet per second squared. And a pound second squared per foot is a slug. Yikes. And this is going to end up with 0.211 slugs. Very exciting. Our rectangular prism. Okay, so we're ready for the calculation of the mass moment of inertia of object number 1 here. 1/12. The mass is 0.211 slugs multiplied by this geometric constant that we need to sort of keep things straight. And here, the cross-section associated with this area is 2 by 2. And I'm going to actually have to convert to feet here as I move through, because the unit slugs, we use the gravitational conversion with feet. So make sure to use feet here. So we're going to have something like 2 inches divided by 12 inches per foot squared plus 2 inches divided by 12 inches per foot squared. Okay, very exciting. So give me a resulting mass moment of inertia of object number 1 when all is said and done of 0.000977 slug feet squared. Gross. God. Ugh.
On the exam next week, are you going to give us something where we have to convert all the way to slugs, or are you going to give us like metric, or at least give us the slugs?
A question in my ear. On the exam next week, are you going to force us to use English units, or will we have metric units throughout? You will not have anything associated with slug calculations on the test. But I might ask you English units for like a different problem that's not as ridiculous.
Thank God.
Thank God, says our Brazilian friend. Okay, continuing. This is our contribution just from object number 1. All right, now let's move to objects 2 and 3. Right. So here we are with objects 2 and 3. We have these right cylinders that have radii of 1 inches, and it's got a 3-inch length. Okay. Additionally, we should note, and this will be important in the future when we're doing parallel axis theorem, is that the y-axis for this problem, which is the axis that we're interested in, and the y-axis of each one of these cylinders is going to be something like, you can sort of tell by the image, half of this width of the square, which is 1 inch, plus half of this total length. That's going to be something like 2.5 inches. Okay. We're going to need this when we use the parallel axis theorem to relocate the contribution of each one of these cylinders to the y-axis from its own centroidal y-axis. The parallel distance between those y-axes here is 2.5 inches. So something you're going to want to sort of keep in mind. Okay, so the same general idea here is something like IY object 2, we'll stick to first, is the mass moment of inertia of object 2 about its own centroid, plus the mass of object 2 multiplied by the distance that object 2 is squared from the axis of interest to the centroidal axis. Okay. This we just talked about, it's 2.5 inches. I'll just kind of leave that be for now. The mass of the cylinder, I don't know yet. I'm going to have to go through that same annoying kind of calculation. And let's talk about this guy here quickly. It's the centroidal mass moment of inertia about the y-axis. For this, get thee to the chart once again. And in this situation, you're going to want to look at this, proper cylinder. And in this particular situation, the axis of interest for us is this y-axis, which kind of like runs along under the center line this axisymmetric plane, this YZ plane in this particular image. So you can look at IY or IZ, they're equivalent. And it's going to be something like 1/12 m times the quantity 3 times a squared, where a is the radius of the piece, plus the length squared. Yikes. All right. But that's okay, we can do it. So I'm just going to copy that down here quickly. Okay. Now, before we go through this, we obviously need to do our mass calculation again. So let's do our mass calculation of object number 2. Okay. This is going to require the volume of number 2, which here is pi times the radius of object 2 squared multiplied by the length of this particular cylinder. I'll work in feet again because my gravitational constant typically uses feet as a conversion when I'm working in English. So pi times the radius we showed before is 1 inch. Here I'm going to normalize so that we work in feet. Squared times the length of my cylinder is 3 inches. Again, converting to feet. We can calculate a volume of this guy, 0.00545 feet cubed. I'm not going to beat this to death. We'll just kind of get to the final answer here. The mass is going to be, the weight normalized by gravity, where the weight is the specific, sort of the specific weight, typically given as gamma, multiplied by the volume, divided by a gravitational constant. We already kind of went through this. You'll work out that one of these cylinders has a mass of 0.0829 slugs. All right. Now let's look at that mass moment of inertia, finally. Let's do the centroidal portion for object number 2. Here's 1/12 the mass, 0.0829 slugs, multiplied by what is 3a squared plus l squared. So this is 3 times the radius, working in feet, 1/12 squared, plus the length squared, again working in feet. We get the centroidal mass moment of inertia of this particular object. It's going to be, again, a very fun value, 0.000576 slug feet squared. That is the centroidal mass moment of inertia of object number 2. Since the cylinder, which is object number 3, has the same general dimensions and is made of the same material as object number 2, I'm just going to write here, this is the same as mass moment of inertia about the y-axis, object 3. All right, so remember this is the centroidal mass moment of inertia of these right cylinders about their own y-axes. So finally, you need parallel axis theorem to get contribution. About this global y-axis. And if we remember from our picture way up, that the distance both for object 2 and for object 3 between the y-axis of the individual object and the global y-axis for both of these cylinders is 2.5 inches. So, contribution for object number 2. Looks something like 0.000576 slug feet squared, plus the contribution from relocation of this guy, which the mass of the guy, you remember, 0.0829 slugs. Times the distance squared. Okay. I don't know if I actually calculated that directly here. No, I don't actually have this calculation. Well, that would be the contribution for object number 2. And note that same for I, Y, 3, since they're both the same. So finally, all together, you have the summation of these guys, which looks like something like here we are from the first guy. Plus 2 times the contribution from here. I'm not going to copy it all back down. I think you guys get the point. Finally, your global IY, 0.00933 slug feet squared. English units are the best, yes. So I know it's a little long, it's a little cumbersome, but the process is the same. Same thing you do for the centroids, all right? What's the contribution of this particular object? What's the contribution of this object? Maybe I got to relocate it to an axis of interest using parallel axis theorem, so on and so forth. Make your way through and just keep track of the numbers. Make sure that it's clean. All right, so I got 438 now. Let's say come back at 445, 7 minutes from now. Ooh, 439 right now. So we'll come back at 446 and resume the lecture with new notes on motion. Oh my God, finally. Motion. Okay, I'm a minute late. Wake up. Wake up. It's time to do some real dynamics. Finally. Oh my gosh, after all that stupid nonsense we have to get out. No, it's not stupid. After all that other stuff we have to get out of the way, it's like all one preamble into motion. It's a little bit frustrating, but okay. Here we are, back to reality. Oops, there goes gravity. So I did post a new set of notes on rectilinear motion. So if you want to go ahead and get that up, you can do that. I want to just kind of talk through the first couple slides on rectilinear motion because I have some information here that I'm not going to test you on, but I think it's just general good information for you to have as a student to kind of get a whole picture of where you are in 2002 in relation to your full like mechanics education. All right. So up to now, you've kind of been working through statics, right? Even when we were doing the friction stuff, that was really still kind of a static analysis. Some of the forces is zero, some of the moments is zero. It's kind of been your life with your mechanics sequence so far. Now we're about to transition to some of the forces is equal to mass times acceleration, and what we talked about before, which was Newton's second, analogy for his second law for angular motion, which is some of the moments equals I times alpha, where I is the mass moment of inertia. You know what that is now. Alpha is the angular acceleration. Okay. Now there's two kind of categories of dynamics, and we're going to look at both of these in pretty good depth. The first we're going to talk about is kinematics. And you've probably done kinematics analysis in the past if you've ever taken any like elementary high school physics class. If you've done like constant acceleration equations where you're looking at how a particle moves, you've done kinematics. Maybe it hasn't been called that, but now you know. So kinematics generally is defined as the relation of displacement, velocity, and acceleration, and time. So I'm sure if you did constant acceleration equations, you had all four of those variables which popped in, and you sort of calculated, what is the trajectory of my ball if I throw it here? All right, that's the kinematics analysis, right? You'll get a lot of that in this class. We're going to treat it in a much more thorough manner using proper vector analysis than you've probably seen in the past, but it'll be very similar to things that you've probably already seen in elementary physics. That differs from what you probably have not seen yet, and that is kinetics. So your kinematics, you're talking about displacement, velocity, and acceleration in time, but you have no relation or no idea how that velocity, that position came to be in the first place. Kinetics tells you how your acceleration and your velocity and your position came to be by discussing forces and moments that act on your object. Okay, that's the difference between kinematics and kinetics. So kinematics is basically just like all the analysis involved with the motion, and then kinetics is how that motion began in the first place. Okay, so it's the relationship between forces and moments acting on a body, the mass of the body, and finally the motion of the body. I bet you have probably not seen this very much. You're going to get a sprinkling of it in this class. You're going to see a lot more of it in the next dynamics class, which is ME2003. All right. Now, we're just kind of tiptoeing into dynamics, but there's a lot of dynamics that MSOE has to offer. And I just want to go through all the classes where you start to see dynamics. Maybe you've done dynamic system. Are you guys in dynamic systems right now? Yeah? No? No? Okay. Well, you'll get there soon. Dynamics of systems obviously has dynamics and a lot more time-dependent modeling of things that are happening. When you get to 3103, 3104, that's fluid mechanics. You're going to talk about the dynamics of fluids and how they move. When you get to ME363, the design of machine components, you're going to talk about how dynamics affects sort of the failure of potential machine components, which is always kind of an interesting phenomena. And then finally, there's a lot of electives that have dynamics. I won't dive into all of them. There's a kind of a list here. So if you end up enjoying this sort of analysis and this sort of things, maybe these electives are for you and in your future. Okay. So there you go. There's your introduction to dynamics and what we're about to venture down. And the first thing that we really need to rock home and rock solid is kinematics, and that is the relationship between position, velocity, acceleration, and time. And that's what we're going to begin right now. All right, first thing we're going to start with here. Rectilinear motion. And we're going to keep it simple to start. And I'm guessing some of this will be redundant with things that you've seen in a physics class, but, bear with me. You'll learn my notation when we go through some of this easy stuff, and we'll kind of get all on the same page. All right. So particles that move in a straight line are said to be in rectilinear motion. Okay. So we like coordinate systems in engineering, and we will use a coordinate system to sort of define, for now, our initial tiptoeing into our motion. All right. So let's first define a one-dimensional coordinate system with origin at O. And we'll have one direction here, which is like the positive x direction. Okay. And we'll say that we have some particle that's traveling along that path, represented by a point P. That is the point P. All right, so what you want to kind of like envision in your head is you've got this one-dimensional line upon which this particle travels. You've got some point which you're defining as like the zero, the reference point, you know, which we typically call like an origin. And let's say that there's a particle that exists on this particular line and it's in motion. It exists somewhere on this line in space. We're going to call that particle point P. And this particle is moving back and forth along this line with some motion. All right. We would define the position of this particular particle using traditional definition of position. And in this particular class, when we're talking about one dimensions, we'll say that that particular particle is located at a distance x away from the origin. So particle moves along line that's function of time. And we typically represent the position of that particular particle with a position vector. And it kind of has a lot of different orientation and a lot of different ways that you could represent a position vector. I like to use the letter R. Okay. For a one-dimensional coordinate system, the position vector is just going to have one unit vector used to define that particular location. So in vector notation, position is something like the position vector R is this location X in the I hat. Pretty straightforward. But most of the time, this position X is going to be some function of T. For example, something like the position vector X, which is a function of time, might be, let's say, 4t squared minus t cubed. Okay? Might be a way for you to define where that particle is at any time step. Remember, we live in this four-dimensional world. The three dimensions you can see and the time stamp that you can't. Though as you get older, maybe you can feel it. I feel it in my hips. Just kidding. Okay, so might see your position vector now is a function of time, which might look something like where that location of that particle is as a function of time in the I hat. Now, when we talk about position, we're going to use vector notation, all right? Even though we have this one-dimensional system, and you could represent the position probably just using this scalar value, which is the time-dependent location of x. Once we move into a two-dimensional and a three-dimensional coordinate system, we want to be able to express the vector with these rectangular components in x, y, and z. So I'm just going to get you started in these, methods early on, right? So there's your position vector. Now, that's position. Next is to consider the velocity, right? And I know you guys probably seen this before, but I'm just going to hammer it home, and we'll talk about velocity. All right. So as particle moves from location r as a function of t, my position, to r t plus delta r t, over some time interval delta t, then the velocity is the change in your position normalized by the change in time. Right. So how long did it take you to move from position 1 to position 2, divided by the amount of time that it took you to get there? Right. So that is one general way to look at it. If you want to visualize this on your little timeline, not timeline, position line. Here we are at P, and we're going to move to another location that's like P prime. Then the distance here that we move is this change in the position vector, delta r. And it occurs over time, which is delta t. This is kind of the discrete form up here, where you would say you had some measurable change in position divided by some measurable change in time. And more often, we would represent the velocity as an instantaneous velocity. This is like what you read in your speedometer in your car. So that above equation is an average velocity over that particular time, delta t. For instantaneous time, instantaneous velocity, take the limit of this equation as time goes to 0. So what I'm doing is the velocity vector is the limit as time goes to 0 of the change in the position vector as a function of time divided by the time step. So how much did your position change over that time interval? Take that time interval down to infinitesimally small amounts of time, and you're going to calculate what your velocity is. All right. Usually this is written as in the differential, change in the position vector dr dt. Where usually this is obviously some function of time itself. All right. Again, this is a vector. With magnitude and direction. Okay. Your textbook, disappointingly, is very lax about representing velocity as a vector, especially when it's doing one-dimensional analysis. It'll write just something like v equals a number, and that just irritates me, okay? Because you need to be precise with what you write in your language, all right? Despite my area moment inertia, mass moment inertia in the homework. Shh, don't tell anyone, okay? Being particular about defining a vector as a vector and as a scalar is going to be important, and it seems a little frivolous when we're in 1D, and that's why your book is so blasé about representing it that way in 1D. But when we move to 2D and we move to 3D, it really has to be there, okay? Because you have to talk about a particular directionality with your velocity, because there's no longer just one path that you can go. You have many different paths that you can move along. And so, yeah, really moving forward, be careful about representing vectors as vectors and scalars as scalars, okay? And end of soapbox rant. All right. The magnitude of the velocity is the speed. Starring Keanu Reeves. And Sandra Bullock. Great movie, 1994. What's that? Ooh, Sabrina watched Speed over break. Give it a rating, 1 to 10. Okay, I need an analytical value. I'm an engineer. 7, very, very healthy rating. It is a good movie, no doubt. Magnitude of the velocity is the speed. Sandra Bullock and Keanu Reeves approved. That is, the magnitude of the velocity is the speed, capital S. I'm never going to write it as capital S. You'll always see me write the magnitude of the velocity as the magnitude of the velocity. All right, but your book has it, and I want you to be aware of it, so I'm writing it here. All right. Pushing forward. I know we're getting a lot of information here, but like I said, your book is rather laissez-faire about their vector versus scalar treatment. And when we talk about the derivative of the position vector, we should probably talk about differentiation of a vector and how it differs from differentiation of a scalar, okay? So, when you're doing your calculus classes and you're talking about differentiation, you're usually doing differentiation of time. Time is a scalar value, okay? So you don't have to worry about the position of whatever you're taking the derivative with when you're doing something like the derivative of a scalar value, which is time or temperature, if you're working at thermodynamics, etc. These are generally just scalar values. But here we have velocities and positions, and we're taking derivatives of these guys. And we need to be particular about what's happening when we actually do the differentiation of a vector. So I want to have a little aside really quick about actual differentiation of a vector and what's going on. All right, so we have that your velocity is the differentiation of the position vector as a function of time, differentiated over time. All right. You may represent this as something like the magnitude of the velocity in the x direction along I hat, right? Now I want to really go through this vector differentiation here, because I think it's important. All right, so full derivation here. All right, you've got something like your velocity is the derivative of your position vector with respect to time differentiated with respect to time. All right, what this really is like the velocity in the x direction as a function of time in the I direction equal to full expansion here, the derivative of this position vector, which is some x position as a function of time in the I hat. This was our position vector in one dimension. Right. Now, this vector actually has like two different things, right? So you're multiplying like the magnitude of the position, x, which could be a function of time, multiplied by the unit vector along which it acts, this I hat direction, right? So we actually need the product rule to expand this. Right? So in actuality, your velocity in x in I hat is something like the derivative of the first bit I hat plus the second bit multiplied by the derivative of the second bit. All right, u dv plus v du, right? You guys learned this in calculus, I'm sure. All right. This here, this is your magnitude of your velocity in the x direction. Right? These guys are sort of one and the same, right? And the reason why I really want to expand this out is because I want to talk about this derivative here, right? The change in the unit vector I as a function of time. What is this derivative? You have a fixed coordinate system. How does the unit vector I change as a function of time? All right, here's my coordinate system. My unit vector I is here. It's a vector of magnitude 1, which emanates from the origin. Does that change at all as my particle moves? No, it's just this stationary thing that allows us to like just tell us where our particle happens to be. So the time derivative of a unit vector is 0 in this instance. Okay. Your coordinate system is fixed in space. The location of the unit vector that's pointing in some direction isn't changing over time. Not in this position, not yet. When you get to advanced dynamics and you're talking about moving coordinate systems, then maybe, but not right now. Okay. So this is what you end up with. Right. And all of this to basically say that, you know, we're in the same general direction here, so we're in the same basis. And it might generally say that here, that our velocity in the x direction, which is a function of time, is the derivative of the position vector as a function of time, differentiated with respect to time. This is specifically for 1d, right? This is how your book typically works, okay? It will show some velocity is the derivative of the position. But this is not the whole story, okay? Because there's like vector mechanics that are behind this that just, the book just drops and it annoys me, okay? So yes, the derivative of the position is the velocity magnitude, right? So the derivative of the magnitude of the position as a function of time is the velocity magnitude in this particular example. So, okay, there you go. So finally, then you can write your velocity is this general form. Okay. This is the clean way to write it. It tells you all that you need about magnitude, direction, proper derivatives, etc. Your book writes just this portion. And that just annoys me, okay? That's not the full velocity. You're not defining the vector, okay? Rawr. Don't do this. Okay, soapbox moment over again. All right, that's your velocity. Similar track for acceleration. One more derivative. I realize I'm going through acceleration, velocity, position relatively quickly. Most people have seen it before, so I'm kind of moving quickly. Okay. So now we have a particle with velocity v at time t. Then later, v plus some change in velocity at original time plus some change in time. All right. The average acceleration of particle over time delta t is whatever that change in velocity was normalized by that time change. So let's say we're using deltas here. The change in the velocity over the change in time. Say the average acceleration. This is a nice form if you have a known velocity change over a known amount of time. Let's say I speed up from 10 miles an hour to 20 miles an hour in 5 seconds. Then my average acceleration over that time is 10 miles per hour divided by 5 seconds, which would be 2 miles per hour per second. Okay. But in this class, we use differential forms. So we're taking as delta t goes to 0. You're going to end up with what is the standard form of your acceleration equation, which is the derivative of the velocity as a function of time. All right, here's your general acceleration equation. All right. Usually it's some function of time, so might see it as this a little bit more precisely. But when you did constant acceleration equations in your physics class, it was not a function of time. Usually those constant acceleration equations just have gravity as the acceleration, which is 9.81, not a function of time. It's just a number. But here we're going to talk about accelerations which might depend on time, and accelerations that might depend on position, and accelerations that might depend on velocity. Crazy, okay? And those situations exist in reality. I mean, as you approach a black hole, your acceleration depends on your position. The closer you are to that black hole, the more acceleration you're going to have, okay? So that's an acceleration that doesn't depend on time, but an acceleration that depends on position. Crazy. Oh, so it's not only a function of time, but it's also a function of distance. And if you're moving fast enough, it could also be a function of your velocity. Oh, God, mind blown. Right? We shouldn't even try to do it, says Peter. No, we're not doing it, all right? Okay, well, anyway. So this is one form that you might see. Also, we know that the velocity is the derivative of the position vector with respect to time. So you may also see sort of an alternate expression here, which is that the acceleration is the derivative with respect to time of the derivative of the position with respect to time, which is usually written as, I need a little more space here, the second derivative of the position with respect to time here. All these are useful. One last one. We know that you're going to have something like velocity is dr dt. Sorry, let's be a little bit more. I want to be clean. Velocity as a function of time is the derivative of the position vector with respect to time. Can rearrange this using some differential equations techniques, which I'm not going to get too much into now, but could rearrange this as dt is the derivative of the position vector with respect to time divided by the velocity with respect to time. This is a little bit difficult to wrap your mind around. But you can actually plug this into star above, which is this guy. So we're plugging in here. And you'll find that the acceleration can also be written, which is a function of time, as the velocity is a function of time multiplied by the derivative of the velocity with respect to time, normalized by the derivative of the position with respect to time. That one's going to blow your mind. We're going to work with this a little bit later. I know that's a little crazy, but You've done triple integrals, so, you know, no problem here. This is only a single differentiation. It's not even an integral. Come on. All right. So these alternate expressions may be useful for not the condition where your acceleration is a function of time, as we were sort of espousing before. Acceleration, which is a function of position. Acceleration, which is a function of velocity. And acceleration, which is a function of time. That's typical. Acceleration is a function of time. Okay. So we've written a lot of math. We've written a lot of vectors. Let's actually like do a practice problem or do some stuff with some of this info. Okay. All right, let's look at a quick example. And let's say that there's a particle on line given by position vector, which is the position vector is 6t squared minus t cubed in I hat. All right, this is a one-dimensional motion, which is a function of time. Right? So this tells me more or less where my particle is located at any particular point in time. All right. So at time t is 0, my position is located at 0. After 1 second, it's 6 minus 1, so it's at location 5, so on and so forth. All right, as time elapses, this thing is going to sort of move along the number line. And I'm interested in sort of like graphing the history or looking at this velocity and acceleration of this particular guy on this number line. So I want to plot the position as a function of time, the velocity as a function of time, and the acceleration as a function of time. And because I can't really plot a vector on easily on a figure, we'll plot the magnitudes of these guys. Okay. All right. So velocity. I know my velocity is going to be the derivative of the position vector with respect to time. But I showed kind of from my analysis before that the velocity magnitude as a function of time in I hat is just the derivative of this like x position in I hat. Right, this is kind of the same idea. Since we only have one-dimensional motion, this position vector only has one component, which is like the x component. And so that means this here is basically my like x of t for this problem. What is the position in the x as a function of t? Right. All right, so the derivative of this expression here with respect to time is just going to be 12t minus 3t squared. In I hat. For those of you that have the actual PowerPoint notes, it looks like there's a mistake in the notes. You guys have the notes in front of you? Any of you have the notes? Slide 9, I think the velocity is written as 12t minus 2t squared. Should be 12t minus 3t squared. So if you got the notes there, you can maybe make a note that there's an error in the notes. What's that? Page 9 where it says the velocity. It's written on the notes as 12t minus 2t squared. But it should be 3t squared, not 2t squared. I just kind of caught that. Sorry about that. And it looks like the acceleration is also wrong. So here's sort of the full expression of your velocity here. And I'm more or less going to plot this in just a second, which is this expression. Okay. My acceleration. Is the derivative of my velocity. Or since I know I'm one-dimensional in life and in this problem, my acceleration here is just the derivative of this like Vx as a function of t, this magnitude of the velocity in the x direction. So this is d Vx t dt in the I hat. So my acceleration here is going to be the derivative of this guy, which is just going to be 12 minus 6t. In I hat. It's again written incorrectly in your notes. It's 12 minus 4t in your notes. I just put that in there to make sure you guys are paying attention. Well, at least I caught it. Okay, so I want to plot this guy. Like this scalar acceleration. I want to plot the velocity, and I want to plot generally this like position here. This xt. All right, so let's do that. And I'm going to try to do my best to put them all on like the same time axis. All right, so give yourself some space here and we'll make some plots. Okay, so here's time. Let's do our position here, which is xt. We have velocity, and we have acceleration. Okay. Almost without fail, when I teach this class, and the first time that I do some drawing of the position x as a function of time, it confuses people because we have the x position of our particle on the y-axis of this graph, which is a little bit strange to think about. But what we're doing is we're plotting the position of this particle as a function of time, okay? And there's some kind of critical times that occur here. I'll just sort of make some marks for these guys. And this is going to be 2, 4, and 6 seconds. Obviously, 0 will be an important time also. All right, so let's plot some of these major guys. Start with position. And we'll remind ourselves what the position function is over here. This is 6t squared minus t cubed. My velocity, this is 12t minus 3t squared. And my acceleration, this is 12 minus 6t. All right. So let's go through and plot some of these values and see what we get. All right, my position here. Obviously, the value of 0, we get 0. All right. The value of 2, I have something like 6 times 2 squared, which is going to be 6 times 4 is 24, minus 2 cubed. It's 24 minus 8 is 16. Well, let's bring that down just a touch. All right. At a position of 4, go through the math, you're going to end up with 32. And at a location of 6, interestingly, you're going to have 6 cubed minus 6 cubed, which would be 0. So let's take a look at what this path might actually look like. And you can kind of like figure out the shape of the curve by plotting it or putting in more points or whatever, but it's going to end up looking something like this. Okay. Now remember what this particular graph represents, all right? The y-axis of this denotes the one-dimensional x position of this particle with respect to the origin on the one-dimensional line, okay? So we kind of reach a max position here, location 32 after 4 seconds. So this guy, like, for the first couple of seconds, he accelerates a bit slowly, but then he picks up speed and gets out to a point of like 32, slowing down as he approaches there, and then he starts coming back. And after 6 seconds, he's back at the origin after traversing quite a path to get there. It's like a horse running around a track. You know, he's run around for 1.5 miles, and then he gets back to his position. He's like, we're back where we started. Why do we have to do all that running? Yeah, old Bill again with our horse jokes. Okay. Let's look at our velocity. Here at time 0, velocity obviously 0. Time 2 seconds, we have something like 24 minus 3 times 4, which is 24 minus 12, which is going to be 12. Put in our 4-second value here. 12 times 4 is 48. Minus 3 times 16 is also 48. So this ends up being 0. And at 6 seconds, we actually go way down here to what is negative 36. It's something like, if you want this to be meters, it'd be like meters per second. It's obviously meters per second squared. All right, so this guy looks more like something like this. It's a second order function. Oh boy. He's sort of like dropping significantly here. So there's your velocity function. Lastly, our acceleration. All right, when time is 0, we have an acceleration of 12 meters per second squared. At t is 2 seconds, we have 12 minus 6 times 2, which is 12 minus 12, which is 0. At 4 seconds, we have 12 minus 24, which is negative 24. And at 6 seconds, negative 24. Okay, so this guy is just a linear function. Okay, so why did I go through the trouble of like plotting all of these guys? Well, it's because we know that there's relationships that exist between position, velocity, and acceleration through the derivatives that we just showed. The derivative of one being the other, derivative of, you know, the acceleration, the derivative of the velocity being the acceleration, and the derivative of, sorry, I'm saying that backwards. The derivative of the position being the velocity, the derivative of the velocity being the acceleration. Yikes. And I want to go through this because I think these graphs, as best as I can draw them, sort of highlight those particular situations, right? So since like the velocity is the derivative of the position, then the slope of this like xt is vt, right? That's why I try to show this particular graph. All right, so let's think about this. The slope of this particular x position at location 0 is flat. It's, you know, 0. Okay, and we see that reflected in the velocity, 0. Seems to have its kind of like biggest slope at this particular location. It's kind of like this inflection point for this particular guy, and we see that reflected in the maximum velocity at this particular time. As it approaches its max position, which is like this location 32, it begins to sort of like approach 32 and sort of slow down, and then at 32, it stops and reverses direction. And so at the location 32, we see that it has stopped so that it can start reversing direction, right? And now it's moving backwards. And so we have this like downward slope, and we see that the velocity values are in fact negative on the other side of that particular location, right? So we have these general relationships that exist between position and velocity. It's nice to see that. Right. Similarly, the area under VT is XT. This is like your derivative, antiderivative idea. Okay. So we see here, as we're moving along this velocity function, we're building positive, positive, positive area up until this particular location. And that happens to be where the position is greatest. Beyond that particular location, we're starting to, the area under the curve becomes negative, and now we're starting to lose position now as our velocity becomes sort of a negative value. Okay, so we have these just general relationships between these functions now because of their derivative and antiderivative relationships. You have a similar idea between the acceleration and the velocity. Same idea. All right, so the slope of the velocity is the acceleration. Same idea sort of holds here. Slope generally positive, but decreasing as we go until it flattens out at the location 2 seconds. We see that reflected in the acceleration. All right, generally positive until we reach a value of 0 at 2 seconds. Area under AT is VT. So here, positive area, positive area, positive area. So we're adding generally to the velocity. And then as we start to contribute negative area under the curve, our velocity begins to fall. Always having these relationships. Okay, so it's just kind of a cool thing to see. Actually worked out graphically. All right, I think we'll stop here for today. We're kind of scratching the surface here with motion, and we'll actually start to do some more in-depth stuff next week when we come back, Tuesday. Work on mass moment of inertia stuff, office hours every day, 8 a.m. to 9:30 a.m. Please give that homework a go. You got triple integrals in there. You got cylindrical coordinates, parallel axis theorem, composite bodies, complicated. Exams open everything. Open everything. Internet, MATLAB, book. What's that? Yeah, you're doing it over Teams. Yeah, it's open everything. Yep. So when you take the exam, I'm going to ask you to turn your camera on and point it at yourself just so I know that you're doing your work. But after that, it's I can't do anything. I can't stop you. I don't know what's happening. I can't. Someone could be Googling stuff behind your, like, I don't know. So I just give you everything you want. And that's like kind of how the real world is anyway. Yeah. No. My theory is not, I make it so hard that you can't do it, but the theory is if you sit down and you don't know how to do a problem, you will run out of time. That's my philosophy. You can't go looking on the internet for 30 minutes for the answer to the problem. It's not going to be able to get everything done. Yeah. You got to memorize them all. All right, so here's my theory on this. That's the very old guard mentality, because 40 years ago, it was very valuable for you to have information memorized, right? If you needed to know Bernoulli's equation and you don't know it off the top of the head, you don't have this device in your pocket that can access that information in 15 seconds, right? You would have to walk your A to the library, check out a book and look in the book, find Bernoulli's equation. 30 minutes later, you've got it, right? But that's not realistic anymore, right? Your education shouldn't be about memorization of equations. Previously, that was beneficial, but now your education should be about assuming you have infinite access to materials, and we're going to teach you how to problem solve to figure out what you need to figure out. And yeah, when do I wake up? That's right. Yeah. All right. Have a good one.